Welcome to AI Paper Slop, where we break down the latest and honestly the most useful AI and tech papers for ML engineers and researchers. I'm going to jump right into it. Today's paper is called Vision-OPD, Learning to See Fine Details for Multimodal LLMs via On-Policy Self-Distillation.
Yeah, and it's by researchers from the Institute of Software, Chinese Academy of Sciences, and Xiaohongshu Inc.
Exactly. And the core insight here is that multimodal large language models, or MLLMs, are notoriously bad at fine-grained visual understanding.
Yeah.
Like, they completely miss small details in large images.
Right. The authors identify what they call a regional to global perception gap. They prove that these models can actually see the detail just fine if you crop the image, but they completely fail when looking at the whole picture.
Which is wild. And Vision-OPD solves this by using the model's own, crop condition behavior as a teacher to supervise its full image behavior.
Yep, via on-policy self-distillation. And the big tease here, the thing that makes this a must-read, is that they use just 6.2K synthetic training examples.
Just 6.2K.
Yeah, and a 9 billion parameter model trained with this method beats massive models like Qwen 3.5397b, GPT 5.4, and Gemini 3.1 Pro. And it does it all in a single forward pass, so no slow inference tools.
Okay, so let's unpack this regional to global gap first, because to understand why Vision-OPD is such a breakthrough, we have to understand the failure mode.
Exactly. It's not a vision problem, it's really a focus problem.
It's like looking at a Where's Waldo puzzle. The model absolutely knows what Waldo looks like, but the global context of the busy beach scene just completely overwhelms its attention mechanism.
I love that analogy. And the paper brings in this great piece of specific evidence. They point to a helicopter image example in Figure 2.
Oh, right. The guy hanging out of the helicopter.
Yeah. So when a standard model, I think they used Qwen 3.59b, is asked about the color of the ear protectors on the man hanging out of the helicopter, it confidently hallucinates and says black.
Just completely makes it up.
Totally. But when you give it only the cropped region of the man, just his head, the exact same model correctly says green.
Wow. So the pixels are there, the representation is there, it just gets lost in the noise.
Exactly. And this isn't an isolated incident. On Zoom Bench, there's this persistent 18 to 22 point accuracy gap between regional inputs and global inputs.
And that's across the board, right? Like all the major models?
Yeah, GLM 4.6v, GPT 5.4, Gemini 3.1 Pro, they all suffer from this.
So the industry's current meta has been to just give the models tools, right? Since scaling up parameters doesn't seem to fix the attention gap.
Right, but the authors argue that this is incredibly inefficient.
I mean, if the model needs to zoom in to see the detail, why not just build an agentic loop? Like let it crop and zoom at inference time, kind of like what DeepEyes or time do.
Well, the paper really critiques those thinking with images methods. Agentic tool use introduces massive inference overhead.
Because it has to keep re-encoding the image.
Exactly. Repeated image encoding and multiple model calls. Vision-OPD's goal is to internalize this capability completely.
So it treats the model's regional perception as a privileged teacher.
Yeah, and they distill that sharp focus directly into the model's base weight so you get the same result in a single forward pass.
Which is huge for latency. If you look at the inference speed comparison in Figure 6, Vision-OPD 9b processes samples vastly faster than agentic models.
Way faster, because models like DeepEyes v2 or SenseNova Mars need all those iterative reasoning steps at runtime, and Vision-OPD just skips all that.
Okay, so to train a model using its own zoomed-in view, you obviously need perfectly paired data. You need the global scene and the localized crop.
Right, and getting humans to annotate that would be a nightmare.
Yeah, so the authors built a fully automated pipeline to generate this without any human annotators. Walk us through that triplet generation pipeline.
Sure, so it's 4 steps. First, they run object recognition and segmentation on raw images to find small regions, and they use a specific area ratio threshold denoted as tau.
So they're aggressively filtering out big objects.
Exactly. Step 2, an MLLM acts as a question generator on that isolated crop to create a question, like what color is the vehicle?
But wait, if you ask what color is the vehicle on the full image, the model won't know which vehicle you mean.
Right, which brings us to step 3. The question is grounded back to the full image by overlaying a red bounding box.
Oh, okay.
And they add a spatial constraint to the prompt saying only focus on the objects inside the red bounding box.
That's super clever. And what's step 4?
Quality control. They use Qwen 3.5397b to filter out bad questions. They only keep the ones where the answer has a consensus score greater than 0.75.
And here's where it gets really interesting for me. They only needed 6.2K synthetic training samples after all that filtering.
Yeah, it's a tiny data set by today's standards.
I mean, in an era where labs are just throwing millions of images at models to see incremental gains, achieving state-of-the-art with 6.2K samples is wild.
It really proves that the signal-to-noise ratio of this specific training method is off the charts.
Okay, so we have the data triplets: full image, crop, and question. How do we actually update the weights? Because this is where the architecture really shines for ML engineers.
So they use a dual policy setup instantiated from the exact same MLLM weights.
Okay, so one brain, two different views.
Exactly. You have the teacher policy, which gets the privileged crop input, no distractions.
And the student policy.
The student gets the full image, the red box, and the question. It's the hard mode.
Right.
Then the student generates an on-policy rollout up to 10,024 tokens. And at every single token step, the framework calculates the divergence between the student's next token distribution and the teacher's next token distribution.
Wait, if the teacher and student are the exact same model, why doesn't the training just collapse? Like, doesn't it just become an echo chamber of bad predictions?
That's the trap of naive self-distillation. The paper has a critical ablation on teacher regularization to address this.
Oh, really?
Yeah. They show that if you use the current policy as the teacher, the training literally collapses to near zero accuracy. The model just goes blind.
So what's the secret sauce? How'd they fix it?
Exponential moving average, or EMA, regularization. They use an update coefficient alpha of 0.05.
So the teacher's weights update on a severe delay. It acts like an anchor.
Exactly. The student can explore and make mistakes without instantly corrupting the teacher. And critically, gradients only flow through the student's logits.
Got it. And they use top K logis distillation, right, where K equals 100.
Yes, to save VRAM. And they use generalized Jensen-Shannon divergence, or JSD, with beta equal to 0.5.
Which is better than KL divergence, because KL is asymmetric, right?
Exactly. JSD is symmetric and smoothed, which provides a much more stable gradient when your teacher is slowly evolving via that EMA.
That makes total sense. And this token-level dense supervision beats standard SFT, doesn't it?
Absolutely. Standard SFT suffers from exposure bias. During inference, the model has to rely on its own flawed prefix, not a perfect human-written one.
Right, the training wheels come off and it crashes.
Exactly. And it also beats RL methods like GRPO or DAPO.
Because those only give scarce sequence-level binary rewards, like a thumbs up and a thumbs down at the very end.
Yep. They don't tell the model which specific token or attention shift was the right one. Vision-OPD's dense supervision gives credit at every single step.
The framework is super elegant. But the true test for you, the listener, is whether it actually moves the needle on the leaderboards. Like, does it break the model's core competencies?
Well, the benchmark performances are dominant. On VBench, ZoomBench, HRBench, and MME Real World, Vision-OPD 9b scores an average of 75.7.
That's insane. It utterly dismantles open source giants like Qwen 3.5, 397D, which only scored 72.5.
And closed source models, too. GPT 5.4 only scored 68.4.
There's a specific case study in the paper that I loved, the Lake Louise boat example in Table 7.
Oh, that's a great one.
Yeah, so Qwen 3.59b looks at this tiny boat way out in the distance and hallucinates that the number on it is 5 hours based on like common practices.
It literally abandons its visual signal and relies on language priors.
Yeah, exactly. But Vision-OPD looks at the exact same pixels, cuts through the noise, and confidently reads the correct number, which is 15.
It's learned to mentally zoom in. But the most crucial win for practitioners here is generalization.
Right, no catastrophic forgetting.
Exactly. Alternative training methods like SFT on self-teacher or RLVR caused severe catastrophic forgetting on holdout tasks like MMVP, POKE, and MM*.
So their baseline reasoning just degraded.
Yeah. But Vision-OPD maintained or even improved general visual reasoning capabilities. It shifts the attention without overriding the foundational knowledge.
And the ablation studies back that up, too. Generating 10,024 tokens during training was way better than 512, right?
Much better. It just provides richer supervision for the gradients. And top K logits distillation vastly outperformed sampled token policy gradient objectives.
So what does this all mean? It means dense token-level credit assignment is king.
Unquestionably, if you look at Figure 5 in the paper, it shows the ultimate victory. The regional to global gap steadily plummets during training.
So the model actually internalizes the Zoom tool.
It completely learns it.
Which is incredible. And if we connect this to the bigger picture, Vision-OPD proves that an LLM can use a privilege view to teach its baseline self how to process noisy global data.
It's a massive paradigm shift. What happens if we apply this beyond vision?
Oh, wow. Yeah.
Like, could we use isolated vocal tracks to teach audio models how to hear through a noisy room?
Or what about video? Could we use temporally cropped video clips to teach a model to find a single frame in a 2-hour movie?
Exactly. Without having to iteratively scan the whole file, the concept of on-policy self-distillation using privileged perspectives is just this massive playground for you to explore.
It's such a brilliant way to solve the attention bottleneck without just blindly throwing more compute at it. Thank you guys so much for tuning into this technical breakdown on AI paper slop. Keep building, keep experimenting, and we'll see you on the next deep dive.